For decades, people looked at this photograph from August 6, 1945, and assumed they were seeing the mushroom cloud from the atomic bomb dropped on Hiroshima. Modern meteorological analysis reveals a different origin. Because of its immense height, scientists eventually identified this towering structure as a Cumulonimbus Flammagenitus, a fire cloud. It was generated by the massive firestorm that engulfed the city, reaching its peak intensity some 3 hours after the initial blast. When a fire generates enough heat on the ground, it stops being influenced by local weather. Instead, it begins to manufacture its own extreme weather system. On the ground, the formation of these storms is terrifying. The chaotic smoke plume billows outward, blanketing the sun and turning daylight into pitch black. This chart shows the cumulative count of these Pyrocumulonimbus events in Canada over several years. Look at the red line representing 2023. In that year alone, Canada recorded 142 distinct fire clouds, a volume that dwarfs the activity seen in any previous decade on record. As these events multiply across the globe, agencies are now prioritizing the behavior of firestorms to protect communities in the path of the next fire season. A standard ground fire transforms into a pyrocumulonimbus cloud through a specific chain of thermodynamic events. The intense heat of the blaze acts like a giant chimney, driving a massive turbulent updraft that pulls cooler air inward and pushes a column of smoke violently into the sky. As this hot plume rises into the lower atmospheric pressure of higher altitudes, the air expands and cools. Eventually, it cools enough that the water vapor and moisture inside begins to condense into a visible cumulus cloud structure. This condensation process releases latent heat, the hidden energy discharged when water vapor turns into liquid droplets. This extra thermal energy acts as a turbo boost, making the cloud even warmer and more buoyant, accelerating it higher into the atmosphere. At these extreme altitudes, the temperature plummets below freezing. Ice particles begin to form and violently collide within the chaotic updraft. This massive friction builds electrical charges, which are eventually released as lightning strikes. Through this chain reaction of heat, expansion, and condensation, a fire burning on the surface successfully engineers its own self-sustaining vertical weather system. Once formed, these storms unleash unpredictable chaos back down on the ground. Rain can form high in the cloud, and as it falls into dry air, it evaporates and cools rapidly. This heavy, cold air drops to the surface as intense downbursts, localized bombs of chaotic wind that can blast outward for 20 minutes or more. Meanwhile, the storm's powerful updrafts act like a vacuum, sucking up large, burning embers. These are lofted to immense heights and carried far downwind, where they drop and ignite spot fires up to 30 kilometers away. The danger extends even further through dry lightning. The electrical charges built up in the freezing upper cloud strike the dry earth below, sparking entirely new blazes up to 100 kilometers from the original fire front. Even the base of the fire becomes wildly erratic. The storm sucks in so much oxygen to fuel its updraft that it creates powerful inflowing winds from all directions. This forcefully alters the fire's path, rendering traditional containment lines useless. Pyrocumulonimbus clouds take a manageable surface fire and weaponize the surrounding environment to create an uncontrollable disaster. If you find the complex physics of our atmosphere as fascinating as we do, consider subscribing to the channel. The impact of a pyrocumulonimbus goes far beyond the local landscape. The thermal energy acts like a cannon, firing smoke and aerosols completely out of the troposphere, the lowest layer of our atmosphere, and directly into the stratosphere above it. This high-altitude injection directly rivals the sheer power of a volcanic eruption. Because the smoke breaches the layer of the atmosphere where rain clouds normally exist, the aerosols cannot be washed out by precipitation. They linger up there for months. Once in the stratosphere, these smoke plumes spread globally. They reflect incoming sunlight back into space, creating a cooling nuclear winter effect at the surface, while simultaneously damaging the delicate ozone dynamics over the polar regions. We've seen this play out on a massive scale. The Australian Black Summer fires in 2019 and the relentless 2023 Canadian fire season both pumped immense volumes of smoke into the global stratosphere. A localized ignition in a single forest can ripple outward, altering the chemistry of the upper atmosphere and shifting the global climate. The Earth and the sky are inextricably linked. Meteorologists are now moving beyond simple observation, applying new understanding of atmospheric physics to anticipate these events before the smoke even rises. Teams at the Desert Research Institute use Earth system models, massive simulations calculating our planet's physical and chemical interactions. By inputting emission data and moisture profiles, they replicated the thunderhead generated by California's 2020 Creek Fire. Simultaneously, the Naval Research Lab relies on data from JPSAS satellites. The Joint Polar Satellite System is a network of environmental satellites that orbit the Earth from pole to pole. By monitoring atmospheric instability from space, researchers aim to predict weather conditions that might lead to a firestorm several hours before it actually sparks. As warming climates and dry fuels transform standard wildfires into atmospheric hazards, these predictive models and satellite arrays provide the hours of lead time required to move families and fire crews out of the reach of a collapsing storm.